All right, so again, I'm going to talk through some of this. So we let P of n represent the proposition, and then the smallest n in this case could be 0. So for P of 0, so P of 0, so you've got a 0 member set, no members, which is the empty set. And we know that has, all right, we're saying it has 2 to the n subset, so in this case 2 to the 0, which is 1 subset. Itself, right? That's itself, that's its subset. So we know that P of 0 is true. All right, so then we move on to the if statement, and my computer's just jumped. There we go, back to the right way. So the if statement being if P of k is true, what does that mean? It means that a k member set has 2 to the k subsets. All right, so let's use that. We're required to prove P of k plus 1. What would that proposition be? That would be a k plus 1 member set has 2 to the k plus 1 subsets. All right, so where do we start? Well, let's start by adding a new member or another object, a new member or another element, a new member to a k member set. So each existing subset is still a subset. So there are 2 to the k of those, and these are all the ones without the new member in them. But we also have, so we also need all the new subsets that are, all the new subsets created when the new member is included. Pen's not going to work. Included into each of the existing subsets. So if we put that new member, for example, into each one at a time, there's 2 to the power of k, again, because they're the same groups there, there's still 2 to the power of k subsets. So in total, because this new member could be in the group, this 2 to the k, or not in the original groups, which is that 2 to the k. So in total, we have 2 to the k plus 2 to the k subsets, which is 2 lots of 2 to the k subsets, which is the same as 2 to the k plus 1 subsets. So again, therefore, P of k implies our P of k plus 1. Therefore, P of n is true for all integer n is greater or equal to 0.